Hello and welcome to today's Talking Medium Voltage. This is webinar number 2 in the series, where today we'll be talking about power outputs, deratings, and general rules around designing enclosed transformers and kiosk substation solutions. If you missed episode number 1, make sure you go over to the NHP MV landing site, nhp.com.au/MV, where you'll find lots of NHP medium voltage resources, including technical webinars, case studies, and you can also find the brand new medium voltage catalogue, which contains over 200 pages of technical fun. So make sure you check that out today. My name is Nicholas Burley and I'm your host today for webinar number 2. And of course, like last time, joining me is a panel of NHP's MV experts. First up, we have Dmitry Lazarchuk, who's NHP's medium voltage technical specialist and has years and years of experience with products and applications in the world of MV. Welcome, Dmitry.
Thank you, Nick.
I'm looking forward to your contributions. Now, we're going to cross over to New Zealand, where we have New Zealand's #1 man when it comes to medium voltage, Mr. Sean Robinson.
Hello
Welcome,
there, Nick.
Sean. Looking forward to what you had today. And then finally, we have Mike Thornley, who will be joining us. Mike Thornley is in charge of the NHP Engineering and Design Department here, and he's going to be talking a lot today about simulation and how to do thermal models when you're designing kiosk solutions.
Okay, so let's get straight into session 2 of our Talking Medium Voltage Demystification webinar. All right, so if we just give a quick review. So webinar 1, we did spend a fair bit of time talking about dry versus oil transformers. And in webinar 2, we're going to be really focusing on power outputs and enclosure design, where we consider things like IP ratings, environments, the types of materials that you can use in when you're designing an enclosure, what sort of standards apply when you're talking about substation kiosks versus just enclosed transformers. Some of the tools that you can use when you're going through that design process, and we'll talk a bit about 3D thermal flow modeling. And then we're going to wrap up today's discussion with a controversial group discussion about, should my substation kiosk deliver 100% output, or do I need to derate it? So we'll have a bit of a look in detail at that. Don't forget, coming up, we'll have our third and final MV transformer discussion, where we're having a close look at designing for harsh conditions. So can't wait for that one, and we'll notify everybody on that as we get a little bit closer to it. Now, before we get into the main body of the presentation, I just want to get across some of what we're calling the general rules of the road. So these are 4 points that we'll expand upon throughout the presentation, but just as general high-level concepts. First point, we don't want to be increasing the IP ratings of our enclosures unnecessarily. Okay, clear reasons: they reduce the airflow, which can lead to either a more expensive or larger transformer, just to deliver the same level of output power. So concept 1, unless you really need to increase the IP rating, don't do it. Just minimum viable product, I would say. What suits the application is what you should be aiming for. Never assume that the enclosed transformer can deliver 100% of the nameplate output. Very important point, and we'll go into detail on that a little bit later on. You really do need to understand the environmental conditions that you're dealing with on the end user site. It has a massive impact on the materials that you're going to be using in the design of the enclosure. And the final design principle is around making sure you factor in the influence of altitude, because these things sometimes are located on the top of a mountain, especially in the case of New Zealand. You'll certainly find applications where things are on top of mountains. Now, there's a few different standards that we're going to be talking about today and referencing. So we've got our AS 62271.202, where we're talking about the prefabricated substations. There's AS 60076 relating to power transformers, and then AS 4312, and we're talking about the corrosion zones within Australia, and Dimitri is going to be talking a bit more about that. So there we go, basic introduction, and you'll see how it ties in a little bit later on. So now what I'd like to do is hand over to Dimitri, and he's going to talk to us a little bit about transformer-specific IP ratings, but really tied into transformer design and enclosures. All right, Dimitri, over to you.
Thank you, Nick. Yes, so we've on this slide we've put this general chart of IP ratings just as a reminder relevant to our discussion today. And okay, we're going to explore what are the typical IP ratings of different enclosed transformer enclosed solution as well as the kiosks. So starting with the cast resin transformers, there are two distinct types of applications. One is indoor and the other is outdoor. Now, cast resin transformer has to be enclosed even if it's used indoors. This is for the safety reasons because the dry type insulation, the cast resin is not safe to touch when transformer is energized. So therefore, we need a basic type of enclosure just to protect people. And this type of enclosure, when it's used indoors, it's just normally IP21. That's well sufficient, and that's the one you can see on the top photo, which means IP21 doesn't provide really any proper protection against water, just protection against vertical drops of water, and it provides the protection from solid objects of 12 millimeters in diameter. Okay, which means you cannot put your finger inside that enclosure. That's the basic level of protection is sufficient for indoor. Now, when we look at the outdoor solutions, it's a different scenario. So when you look at cast resin specifically, as far as solid objects protection, what we want to avoid is an ingress of vermin. And because again, the cast resin transformer relies on a combination of cast resin insulation and the air gaps between the coils to deliver all the dielectric ratings. So therefore, we don't want any large kind of vermin to get inside the enclosure, whether it's small animals or snakes or
maybe frogs.
Or maybe frogs. There's lots of wildlife in Australia all over the place, so we don't want them to live or crawl, inside our cast resin transformer enclosures. Therefore, the IP rating has to increase, and typically it's IP4X. So we talk about 4 with a 1 millimeter, maximum 1 millimeter gaps in the enclosure. Sometimes we've seen customers happy with the 3, which is 2.5 millimeter gaps. So both are quite small gaps, so we won't get any large or medium size type of animal through there. So if ants won't really do much of the impact. So these are the protection from solid objects with the enclosed cast resin transformers. If you look at the second digit, which is protection against water, what we're seeing for as a minimum IP rating is 3. So therefore, it protects against the rain with a 60 degrees angle, which is fine for many areas in Australia and New Zealand. However, the consideration if you have a possibility of a horizontal rain, which is applicable to some tropical regions, that's where better to go with a 4 as a second digit that protects from water shower from any direction. So therefore, the overall IP ratings we've seen for the cast resin outdoor enclosures, IP34, IP43, IP44. So these are the typical IP ratings used. And for us, probably the most common is IP43 as to what we supply as NHP. Now, looking at the oil transformer now. It's a different scenario. Of course, the oil transformer is fully outdoor protected device. So the transformer itself has IP rating of IP66, which means it's protected, fully protected against dust and also against strong jets of water. And that's obviously natural for the oil transformer being a hermetically sealed unit, so it doesn't allow the oil out of the transformer and therefore doesn't allow water or dust in. So that's quite logical. The only other thing to consider there, okay, what happens if we enclose the oil transformer? And this is where we need to discuss around the, okay, why would we enclose the oil transformer in the first place, which will relate to oil bonding. We'll talk about that in more detail in a later slides, but for this slide, important to note is typical IP rating of enclosed oil transformer or a kiosk substation with the oil transformer is IP23D, which is well sufficient for the oil transformer protection and the bond protection against the rainwater. Okay, so let's have
a look at some examples of IP testing. So, Sean, you've got many years experience with design and whatnot of enclosures and kiosks. So why don't you talk us through there's a couple of videos that we're going to play, and you're involved in some testing with a customer over in New Zealand, and I think there's some good examples here. So I'll play this first video, and you can talk to us about the louvers and the arrangement of these louvers. You can see there you've got your hose out, giving it a good spray.
Yeah. So this was a project for a wind farm. The transformers were 2.6 MVA. It's fair to say they were installed in a very arduous environment. It was right on the Cook Strait. And so what the customer found, we delivered 63 2.6 MVA transformers, and some of them were getting water in through the louvers into the oil containment bunding. And so the same customer was involved in a project in Victoria. And so part of the design technical requirements was that they wanted us to change the louver profile to prevent the water getting through and into the bunding. So at the bottom of those slides there, you see the two different types of louvers that were used. Mm-hmm. And so this is part of our testing to see how effective the new louver type was at preventing water getting through. So if you just want to play that second video for me, Nick.
Mm-hmm. There we go.
So yeah, what we're looking for is in behind the louvers, we've just got some cardboard where you can see on the first video there was water getting through and making the cardboard wet. In the second video, you can see that the amount of water ingress through the louvers is almost zero, even though in this instance we're using a fire hose, so there's pressure involved. Effectively, those louvers were keeping out the water from getting into the oil containment. But to give you a fuller picture, the transformer for West Wind had been temperaturized, tested outside of the enclosure, had been temperaturized, tested inside the enclosure, and then delivered 100% full rating. Because we were changing the louver profile, we redesigned the transformer to basically give another 5 degrees less in the design top oil and winding temperature rise. It just happened to coincide with me going to Europe. So I hop on a plane and get to Singapore and get an email to say that they tested the transformer and we were 7 degrees below what we had delivered for West Wind. So I go, cool, extra 2 degrees up my sleeve. Get to Frankfurt, get an email to say, unfortunately, the transformer in the kiosk now had exceeded the standard as far as its top oil rise. And so in solving one problem, that being reducing the ingress of water into the oil containment, we created another because the louvers were no longer effective at getting the heat away from the transformer that was installed inside. And so just to finish the story, in the end, we had to get a design compensation from the customer to redesign the cover so that we put top hat ventilation on top to get the heat out of the enclosure. So we, in this instance, could get 100% rating out of the 2.5 MVA transformers.
Okay, that's a very interesting and probably an important point we're going to expand upon. So again, they're looking for the 100% rating output to be achieved. Okay.
Yeah, so in that second video there, we saw we were aiming for basically splashes of water all around, and we basically used a fire hose to prove that we were a lot higher than that.
Yeah.
The crazy thing is that at the end of getting the type test and everything approved, I subsequently found out that out of the 63 original transformers delivered to Westwind, it was only 3 or 4 of them that were right on the coast that had the water driving up horizontally and through the louvers into the oil containment.
Yeah.
And potentially the problem could have been solved simply by reorientating the position of the kiosk 90 degrees so the prevailing wind hit the doors, but hindsight's 100%.
So just shifting it around might have fixed the problem.
But it's a good example of the fact that you designing kiosk enclosures is, to a certain degree, is a juggling act, and there's compromises that are made.
Sure. No, that's a good point. All right, well let's go through and just quickly, we're going to summarize based around the transformer technologies and the enclosure types, just some of the details, so we're all on the same page around IP ratings and different options for IP ratings. And then we're going to delve a bit more into what does it mean from a derating point, because Sean, as you said there, change the louvers, fix the IP rating. What are the impacts that can have on the output power and the and what a customer should expect from such an arrangement. So Dimitri, can you talk to us a little bit about cast resin transformers and IP ratings and what typically people see in the industry?
Yeah. So it's good to summarize what just recently said. The cast resin transformer on its own is IP00 device, so it's not protected against weather conditions. When it's used in indoors, has to be housed in enclosure for safety reasons, which is an IP21 enclosure. When it's used outdoors, the typical enclosure IP rating is IP43, that protects against vermin and against the rain. And if you have a horizontal rain scenarios, then you need to go to IP44. Okay, let's look at the oil transformers now. We mentioned that the oil transformer on its own, the tank of oil transformer is IP66. It provides a full protection from the environment. The cable boxes of oil transformer has slightly low IP rating, which is IP56, which is again fully adequate, which means it provides protection against strong jets of water and protection against dust with a limited ingress permitted. So this is a technology for oil transformer, but there's one problem with application of oil transformers is that you have to consider potential oil leakages, and therefore, well, there's no ideal transformers. Over time, all the gaskets deteriorate. It's quite possible they're going to happen at one point or another. So the common method to actually avoid environmental damage and spills of the oil into the environment is to provide the oil band. And oil band is requested, as far as I know, in Australia by almost all customers. Now, the challenge with the oil band, if it's just an outdoor transformer pad mounted, okay, the band can be made out of concrete, but that band gonna fill with rainwater. So the rainwater stays there, for a while, and at the same time you have a leakage of oil. Therefore, the band will no longer work effectively. So it's will start filling, being filled with rainwater partial and then filling with oil. The oil will eventually spill if the leakage was a substantial one. So that creates an issue, and more customers is now concerned about this issue these days, that how we protect a bund against the rainwater ingress. There are two solutions we've seen in the industry, and one of the solutions is there are special filters available that you install in the outdoor bund that allow to segregate between the oil and the rainwater. The solutions are there. We haven't used them ourselves. There are, it's not that all easy because you still have to drain that rainwater. So it's quite a complex solution. The other option that we're seeing quite often and being requested by the customers, and this is what we supply ourselves, is the enclosed oil transformers. So really the purpose of enclosing the oil transformer is the only purpose is to prevent oil bund filling with rainwater. And same happens if you have an oil transformer inside the kiosk substation. So we have the oil bund inside that enclosure. And I'll pass it over to Sean to tell an interesting story about this oil bunding.
Yeah, thank you, Dimitri. So this is a current project that we're working on in New Zealand, where the photo on the left is, I guess, a fairly typical industry solution from a bygone age, where you've got a concrete bunding that's sealed. You've got an oil-filled transformer. As Dimitri said, you've got to have some way of being able to drain or separate the water and the oil. And so, often solutions like that are only as good as the maintenance. And, certainly in this particular installation, the environment, there's a lot of rain. And so, potentially, it's a solution that the customer doesn't, going forward, want as their standard solution. And so we are supplying a oil-filled, well, in actual fact, it's an ester-filled transformer inside an enclosure with an oil bunding. So the red line that you can see there is the oil bunding with the transformer sitting inside it. But some of the design criteria that we had to consider was the fact that because it is a outdoor transformer installed in an enclosure, we need to ensure that it gives 100% output based on its nameplate rating. And so therefore we have designed the transformer to basically give us a 15-degree sealing. So instead of a 60-degree top oil rise, the transformer's been designed for 45 degrees top oil. The winding temperature, instead of being 65, has been designed for 50. And so that when it goes into the enclosure, it will still be able to provide its 100% nameplate rating. Interesting enough that the customer in this instance is still aware that even though we've gone to a lot of effort to ensure that there won't be any ingress of water into the bunding, it's still fitted with float switches just on the off chance that there is an oil leak or water, so that they can basically ensure that they don't have an issue with respect to oil getting into the environment, or, as I said, esters in this case, because the transformer is actually being installed in a national park, so it has a lot of waterways. So it's the company's very environmentally sensitive, and so so this is the solution that the customer has decided on compared to the photo we see on the left-hand side. I guess they could have just simply got a standard oil-filled transformer and used the same bunding, but they've been quite progressive in their view, and they have now got that standard outdoor oil-filled transformer sitting in a bunding inside an enclosure.
Yep, excellent. So that's an outdoor approach. So Dimitri, why don't you tell us a little bit about this picture?
Yeah, so this picture is an example of one of NHP kiosks we've been supplying, and you can see that the oil transformer sits there on the bund, which is the white metal part at the bottom of the transformer. So this is what this is how the solution looks for the kiosk substation, and in essence, it's the same concept as for the outdoor enclosure for oil transformer. Yeah, one difference though when we talk about the substations versus the enclosed transformer is the attitude to derating, which we're probably going to talk in the next few slides.
We certainly will. Hey, Dimitri and Sean, do you like demonstrations of electrical equipment by expert presenters?
Do we get to blow stuff up?
Nick, I absolutely enjoy it as long as it's medium voltage.
But Dimitri, there's lots of other things in life apart from medium voltage.
Really? What
Yeah.
are they?
The NHP Power Hub has a wonderful cubic board. It's type tested and you can demonstrate arc flash and what happens.
Sean, but has it got the arc killer? Look at the medium voltage switch gear. This is an arc killer switch. It's going to kill the arc in 50 milliseconds. That's a technology that works. Medium voltage is the stuff.
So if you'd like to come down and see all of Dimitri's MV switchgear and maybe a few of the other bits and pieces in the low voltage section and automation, make sure you check out the Power Hub today. It's located at the NHP head office in Richmond, Victoria. Dimitri can even come down and show you his arc killer.
Absolutely.
All right, great. Thanks for that, Dimitri. Now, what we're going to talk about now is substation kiosks, derating, and some of the differences that you've got to appreciate between derating in a substation kiosk versus an enclosed transformer. And we've got some good examples that we'll go through. So, Dimitri, what can you tell us about the kiosk substations, the IP ratings, and how to apply some derating?
Yeah, so for the kiosk substations, maybe let's start with the definition. And a kiosk substation is a substation that contains the HV switchgear, the HV to LV step-down transformer, and the LV switchboard. So within kiosk substation, which is covered by the 62271 202 standard, you typically have the following IP ratings. The HV end and LV end of the substation are IP54. It's obviously the protection from environment that is important. And the transformer section, we don't need this high IP rating, and the high IP rating would obviously reduce the natural ventilation and create lots of design issues. So the IP rating acceptable for the kiosk substation is IP23D as per 62271 part 202, which it's a minimum rating, and it's well suitable for oil transformers. For the cast resin, the standard doesn't talk about that specifically, but for the considerations we discussed before, we offer IP33D with the cast resin transformers just to minimize impact of vermin on the transformer insulation.
Okay, no, that's interesting. Now, one thing I did forget to mention, Mike Thornley has just joined us as well, and Mike will be talking to us a little bit about his experience with using thermal modeling software, which will come up in a couple of slides' time. But hello, Mike. Thanks for coming on the call today.
Thanks all.
Excellent.
Right. The other topic I want to discuss here is the difference between the kiosk substation standard and the transformer standard with regards to the derating. And that's very important to understand. What people don't realize, that in a kiosk substation as such, the derating of the transformer is allowed by the standard. And therefore, the rating of the substation is called the maximum power of prefabricated substation, but it doesn't mean it's going to deliver rated power. Why? Because the rating of prefabricated substation is equal to the rating of the transformer itself. However, once we put the transformer in enclosure, it will be derated because enclosure creates additional temperature rise. So the difference with the other standard 60076, which covers transformers only, that standard doesn't allow any derating of the transformers, whether it's enclosed or unenclosed. So that's important difference to understand. The reason for that is when a transformer is delivered in the enclosure, it's assumed it is delivered like that from the transformer manufacturer, and therefore manufacturer has to make sure that that enclosed transformer does deliver full 100% output, and therefore they have to slightly upsize the transformer within enclosure itself, but that's not relevant to the end user. So they expect 100%, and this is what the standard tells. While in the kiosk substation is assumed that transformer is purchased from manufacturer, and then a third party builds a kiosk substation by adding the LV end, HV end to the substation. And therefore the original transformer does not consider what's going to happen inside the substation, and therefore the standard allows the mechanism to actually derate and calculate the performance of that transformer within the substation enclosure. So if we go to the next slide, Nick, we'll see exactly the method shown there with the graphs. So first of all, the standard defines enclosure class. And what is class of enclosure is essentially the temperature rise that will happen inside that enclosure when it's loaded to 100% output. So if let's say if enclosure class is 15, that means the temperature rise inside the enclosure versus the outside ambient temperature is going to be 15 degrees. The way to determine temperature enclosure class can be either by modeling or by testing. And there is a type test method defined in the 62271 standard how to measure enclosure class. Why we need enclosure class? Well, to use the graphs below and find out what's going to be the derating of the transformer within the substation. So obviously the higher enclosure class, the higher derating will be. And in this particular example, we'll look at enclosure class 15 and the derating to 90%. So in such substation, the transformer will deliver 90% of the nameplate out. Of course, you have to select, there are different graphs depending on insulation class of the transformer itself. We selected here the graph for the insulation class F, which is typical for the cast raising transformers used in the industry and including NHP cast raising transformers. And there is another similar graph for the oil transformers on the right-hand side. Okay, so the bottom line is that if you're ordering a kiosk substation and specifying a kiosk substation rating as, let's say, 1.5 MVA, do not expect that the output of this substation is going to be 1.5 MVA, because this is what the industry would typically offer. That the supplier will typically, unless you specify exactly what you want, the supplier will install the standard transformer into that substation, which will be rated 1.5 MVA on the transformer nameplate, and then the whole substation will deliver a reduced output depending on its design. So all these details they need to be considered during your specification stage, and also ask suppliers to provide it clearly on their offer what is the enclosure class or what is going to be the output of the kiosk substation.
Okay. Any other points on this slide you want to run through, Dimitri, or we'll keep rolling?
No, I think we can carry on to the next slide when we'll talk about the enclosed transformer on its own and the derating or the fact that it's not allowed. So we have a recent project example where a customer originally requested just a 2.5 MVA oil transformer. Enclosure was not specified at the original quotation stage. Then they placed a purchase order for a transformer, and then it became clear that the end user wants a transformer to be enclosed. This is where the challenge is. All the calculations were based around transformer delivering 100% output, which is exactly what the standard for the transformers would require. So that's a fair request, but the fact that it's going to be enclosed was not considered. So therefore, the transformer was not designed to accommodate additional temperature rise within enclosure. That was specified in the beginning. It would have been designed that way, and therefore the combination of transformer plus enclosure would still deliver 100%. as required by 60076. So this was not the case, and therefore customer asked us to help and try optimize the enclosure design and minimize the enclosure class, so minimize the temperature rise and therefore minimize the derating of that transformer, which is what Mike and his team has worked on. And I'll pass it on to Mike to talk through the details of thermal flow modeling that they did and how they achieved the target class 10 of this transformer enclosure.
Just to set some context, so you worked for NHP for many years. Roughly how long do you think?
Ooh, 12, I think.
You are in charge of the engineering and the design team for a lot of the work that gets done within NHP. And this, getting involved in this particular project, you went down the path of having a look at how we can use software to be a bit smarter about the initial design. So why don't you start by telling us a little bit about the software and why you decided to use modeling software to help optimize the design?
Okay, so we know from what Dimitri said that we need to get a very, very good class rating. Class 10, which is what they're aiming for, is very difficult to achieve, and it'd be difficult to achieve anything better than that. Certainly can't achieve class 0. So we are aware that to get the best cooling effect on the transformer, we need to have good air entry flow through the bottom vents. We need to have good direction of airflow over the transformer, over the parts that need to lose the heat. And then we need to get that hot air out of the transformer as quickly as possible. We want good laminar flow through the enclosure as we can get.
Can you talk a little bit about what you mean by laminar flow?
Laminar flow is really just smooth, even flow. So, without lateral interference, without eddies, without disturbances at all. We want to make sure that the air is moving as quickly as possible through the enclosure. We know if we can get good, quick movement, one, we have the velocity, so we're getting air out as fast as possible, but as soon as we can get high volume of air through the enclosure, we know we're getting a lot of heat out of the enclosure. And that's really the key for the software, is we're looking for refining the performance of the enclosure, performance of the venting system, to make sure we can maximize that airflow. And how do we do that if we're just building designs and prototyping? We can build something up, make assumptions, test it, but how do we make refinements? And the key thing about the software is that you can make small tweaks, and you can actually do cross sections and see the eddies and see the effects of how the flow is working. And you can see on this diagram here, it's actually drawing essentially lines to show the airflow. So we know we have lines that are running largely parallel to one another. We've got good laminar flow. Not always going to get it.
We've got a couple of slides where we go into a bit more detail on each of these through the design and modeling path that you've followed. Okay, Mike, so what we've got on this screen here is some detail around the original kiosk or enclosed transformer design that your team came up with, and then we're cross-referencing that to the final design that was achieved. So if you can talk to us a little bit about what we're seeing here on the screen from the original design, and then the types of changes and improvements that it allowed you to implement.
Okay, so we can see on the left that the transformer, by the colours, is showing that the main core is where the heat's coming from, and then that core is radiating out through the fins. And what we have with our initial design, as I mentioned before, we have air running in the bottom vents through over the transformer and out the ridge vent. But what we found there through this modelling is that we aren't really getting air out of the top as fast as we need to. And the temperature of the air within the enclosure around the roof space is high. It moves itself down, and it's moved down enough you can actually see venting out of the lower inlet vents. And the last thing you want is to have air coming in and out of the same spot. So we know we've got issues if we still have that. So, and we also know that the high air temperature around the transformer is not going to do the transformer any help at all. With the right-hand design, with that knowledge, we can look at how we can improve the ridge vent design. So we've improved that ridge design. We've had a better laminar flow, higher velocity. And one of the great things about thermal modeling is, you don't always just see the direction of the air, but you can see the velocity of the air, so the actual speed of it. Obviously, velocity is direction and speed. We found that we still weren't getting enough out of the ridge vent, so we end up opening up the eaves of the enclosure, so you can see air coming around under the eaves and flowing out. And as a result, the transformer temperatures come down. You can see the colouring. We've gone from a red in the core to more of an orange in the core, and we know through the numbers that we get from this modelling that the oil temperature has come right down. We can also see that the velocity, and you can probably see that with the lines, that the velocity of that airflow through has immensely improved. This is all through making incremental changes to the design and looking at where those eddies occur and looking at where we can improve our structure of the sheet metal and stuff with the enclosure itself.
Okay, when you were doing the design, the concept was to have a natural ventilation and not have fans. You want a good, solid, robust design that's going to do the job and doesn't need to have all other bits of stuff slapped onto the side of it. But just for the sake of the exercise, I know you decided to put a fan on and see what sort of impact that would have. What can you tell us about having a fan included onto the design?
Well, initially to say that the great thing about the software is that you can just make a small change, add a fan to the model of the software, and you get some new results. You don't have to go and build this whole thing up. So what you can see from this is the airflow has increased in velocity. That's what's going to occur when you get forced ventilation. It's a lot more turbulent and chaotic. We've got air coming out all sorts of openings in the enclosure. Yes, you can see from the colouring of the transformer, we got an improvement in the temperature. But what we found is really it wasn't worth adding the fans. We had probably 4K difference in temperature, and we have a whole lot more chaotic flow going on. What we end up finding is that the actual, once we'd refined the venting system, we had really, really good natural ventilation, and that's always the preferred way to go, is just rely on natural ventilation without using fans.
But anyway, interesting results. Now, the final thing here is around the solar load and what that impact is. Can you tell us a little bit about what do we mean by the solar load, and what did you find through doing the modelling?
So solar load is this enclosure is going to go outside. We could ignore the sun, but we really shouldn't. It's going to have some impact from the sun. Sun is going to come down, heat the outside enclosure, and essentially heat the air inside it as well. So the great thing again about thermal modelling is you can just apply a solar loading. You can change directions of that, and you can see the impacts on it. The key that we're looking for here is that the outside skin of the enclosure heats up, the inside air close to that skin heats up, but if you've got good flow again through the enclosure, then that heat just rises up and runs out without having a big impact on the air temperature, which is going to essentially affect the temperature of your transformer. And we've found with this modelling, yes, we get an increase. It's difficult not to have any impact at all, but we'd also found at this point that once the airflow, because it's coming in the bottom vents and running up over the walls and over the transformer, that we could dissipate that heat very, very easily. So we had some impact, but not high enough to really worry about. I guess that the big benefit is that if we hadn't had that good airflow through the enclosure, we may have had to resort to having solar shields, second skin on the enclosure to reduce the impact of that solar loading. That's an extra expense. So what we can see from this study is that, do we need that or don't we need that? We can make those calls now. We don't need to go and invest in it, do more testing, put the enclosure under heat lamps or out in the sun or whatever, and to get some data on it. We can see that from this.
All right,
I suppose just on that, I talked about data and results and numbers. I'm not sure whether you're going to come to this, but really at the end of the day, this is modelling. We need to have a reference design to be able to trust the numbers that come from it. So when we set up the model, there's parameters that we go through to set it up, and we need a reference, a real test to compare those two. Now, we have test data from the transformer manufacturer. They'll often do testing, provide us information about the watts loss of the transformer, about the oil temperature, And we can build that into the model, because we can run this model on an unenclosed transformer and enclosed transformer, and that comes back to this class rating. If we do the same model on either same conditions, we can see that the difference in temperature, which equals your class temperature.
All right, Mike, that was really interesting. Thanks for running us through that.
Problem. Thank you.
Thanks, Mike. So, Dimitri, we've touched on this earlier. I'd like to talk more now about the impacts of the materials. This is probably something that people don't always appreciate. The materials that are used in the enclosure really need to be linked to the application and B, the environment. What can you tell us about the types of materials and how you would go about trying to ensure that the material used is fit for purpose for the environment?
Thank you, Nick. That's an excellent point. And what we found in the industry and in our own experience, that this topic is often overlooked, unfortunately. But there are actually excellent tools and standards available that will tell us what sorts of environments we get in Australia, and therefore what consequences will happen for different types of enclosures. So if we look at this AS 4312 standard atmospheric corrosivity zones in Australia, basically tells us that there are different corrosivity zones depending on proximity of the installation to the ocean. The high zone is C4, C5. This is what you're going to find along the coast in New South Wales, in South Australia, and pretty much along any ocean beach type of coast where you have the surf and the wind is blowing of all this salt water mist towards the shore, and this is where the first couple of 100 meters from that surf beach, the very, very corrosive environment, which is called zone C5, and then also zone C4, which is sort of a bit further. For example, on this map here, you can see that all this coastline around Sydney and up to Newcastle, it's all that red zone C4, C5. If we go through details of this standard, we'll find that the miles still won't be suitable at all in those environments, and therefore you have to find the more corrosive resistant materials, which could be galvanized steel, and even the galvanized steel won't be good enough for the C4, C5. So the best choice is aluminium or stainless steel. So it's very important to consider these factors if you want your enclosure to last, for many years, not for a couple of years. And I'll pass it over to Sean to talk through one example we've seen in the industry, which is on your right-hand side.
Thank you, Dimitri. As they say, a picture speaks 1,000 words. And so the picture at the top was the photograph of the kiosk as it was installed. And the photo down the bottom is what happens when the enclosure and the paint prep and everything else isn't suitable for the corrosion class for where it's being installed. And I guess being in the industry in New Zealand, most of my career I've been exposed to things like geothermal, hydrogen sulfide, very harsh coastal environments. And so for me, knowing that this kiosk was being installed so close to a surf beach, quite clearly it should have never been manufactured out of just mild steel with powder coating. A project I was involved in New Zealand was right on Cook Strait, a place called Westwind, a place called Macra, and literally the salt spray and the rain comes in horizontally. And the kiosks there were galvanized sheet steel. Some would advocate that maybe aluminium or stainless would have been a better solution, but we worked very, very closely with the company that makes the powder coating, Dulux, and through their knowledge, we were able to offer a solution where the galvanized sheet steel was treated and then had a zinc-rich primer put on, then an intermediate powder coating, and then finally a powder coating that was specifically for that environment. And those kiosks have been in that environment, and they certainly don't look like the photo that you've got there.
And just for transparency, so this kiosk was not an NHP kiosk. It was supplied by a different manufacturer, but we're familiar with this particular end user site, and we've got some photos of the befores and the afters. And on another point that you raised there, Sean, around you said you're working with, in this case it was Ulux in the other job that you had. I know, Dimitri, in our experience, when you're looking at powder coating, if you're talking about your typical powder coating that would be applied to an enclosure like this, you shouldn't think of your standard powder coat as being a solution that is going to protect the material underneath, because it's actually, your standard powder coating is porous.
Yeah, that's exactly right, and we have heard this information from the experts on the corrosion, explaining in examples like this one what exactly happens, because when we look at the photos closer, you can actually see that the powder coat itself is not damaged, but what happens, the rust happens underneath the powder coat. And the explanation for that is, yes, the standard powder coat material is a porous material. So therefore, the moisture slowly sort of penetrates through that, and that causes the material underneath to start rusting. Okay, based on this environment, what sort of protection we need to provide for the mild steel, apart from the external powder coat. So maybe if you go to next slide, Nick. I borrowed these graphs from a very educational report from Galvanizers Association of Australia, which we have the link in the bottom of the right-hand slide. What this report tells us is the rate of corrosion of zinc. So if you use the galvanized material for the enclosures like a Galvabond, or if you use a hot dip galvanized material for the plinth, which is what typically used, this graph will show, depending on the thickness of zinc layer and depending on this atmospheric corrosivity zone, how long that galvanized material going to last. And that graph, of course, assumes there's no protection provided by any sort of paint. So that sort of assumes the worst case scenario. If you have using a generic powder coat that doesn't provide much of protection, then this will give you a good estimate of the worst case. And I suppose to put those numbers in a perspective, depending, there are different standards for galvanized materials, and there are different technologies. So the hot dip galvanized materials, the hot dip galvanized technology, provides a much thicker layer of zinc. But even with those, as you can see on the photo on the right-hand side, depending on the standards, the thickness of that zinc is different, and therefore the tube has rusted a lot more than the vertical support, because it has half of thickness the zinc coating. But then when we look more specifically into the galvanized sheet metal like Galvabond, it has even thinner layer of zinc, and which again, looking through all the data sheets, work out it's about 20 micron, which tells us, if you look at this graph, that there's no additional protection provided by the paint or the powder coat, which is the worst case. You're looking at C3 environment as probably a suitable environment for the galvanized material, but the C4 is a lot more challenging. And in that case, our advice on being more conservative is to upgrade to aluminium or stainless steel for the C4 environments.
Okay, thanks for that, Dimitri. We're getting near to the end of today's webinar, so we're going to again have our controversial panel discussion. Should my kiosk substation deliver 100% output, or will it need to be derated? We did talk a little bit about this earlier in the presentation. People's expectation. I asked for a 1.5 MVA kiosk, or I'm asking for a 1.5 MVA transformer. Expectations, and I guess from a supplier's point of view, how to manage those expectations and make sure we're talking the same language between consultant, end user, and the manufacturer. Pretty important. I suppose, Dimitri, the one takeaway that I've certainly sort of commented on here is you need to ask the right questions. So the end user, the consultant, and the manufacturer all have the same understanding So let's have a talk about that, and then we'll look at a real life example where there was a bit of confusion in that space, and how you hopefully can avoid getting into those sorts of situations.
Yeah, exactly. So we already discussed this topic early in the presentation, but let's summarize it again because it's so very important. I've put some snapshots from the 62271 202 standard prefabricated substations, which again, the first one explains what is the rated maximum power prefabricated substation. And it says rated maximum power prefabricated substation is given by the maximum rated power and the total losses of the transformer for which the substation has been designed. In a simple words, what it tells us that the power of prefabricated substation is the same as the nameplate power of the transformer, but this is the rated maximum power. It's not an actual output. So that's very important to understand. And therefore, there is a next clause of the standard talks about rated class of enclosure, and it all comes back to those derating graphs that we looked at. So while your maximum power of prefabricated substation may be 1.5 MVA, but depending on the class of enclosure, you can get only maybe 90% or even 80% of this maximum output. So the actual continuous output at the maximum rated ambient temperature, which is normally 40 degrees, could be, for example, 1200 kVA from a 1.5 MVA rated kiosk substation.
Okay, so let's have a look at a real life example where we had a customer wanting to replace their old oil pad mount transformer. And they're looking for a kiosk substation utilizing a cast resin transformer, and they'd specified that the nameplate of the new cast resin transformer should be the same as the old oil transformer. Okay, so this site was on the coast. They did call for an aluminium enclosure, and the request was for a 1.5 MVA nameplate rating. So Dimitri, tell us how did this particular project sort of go a bit off the rails? Keep in mind this was a long time ago. All right, so you live and learn, as we all say. No one's perfect, but there's probably some good learnings and takeaways for people when they're specifying who are listening to this. What can you tell us about what happened?
That was exactly a classic example of misunderstanding between customer and manufacturer as to what's expected from the kiosk substation. From a customer perspective, they had 1.5 MVA transformer. They've asked for 1.5 MVA transformer, but this time it had to be in the enclosure, within the other components of prefabricated substation. So it became a prefabricated substation. With this request, we offered and supplied the 1.5 MVA cast resin transformer, then installed it in a kiosk enclosure. But then what became clear that customer was actually expecting that it's going to perform exactly as their old oil transformer, therefore deliver a full 1500 kVA output, which of course it's not going to happen when you install a transformer of this rating into the kiosk substation enclosure. So when this misunderstanding sort of became clear, customer has requested to actually provide the information about the output of this transformer in the enclosure. Eventually, we decided to run a type test, which became very useful for us for future reference in our designs of the kiosk substations. But what this type test revealed, and the type test, by the way, was performed in this Lane Cove test laboratory in Sydney, which used to be our major test laboratory for all MV and HV tests in Australia, and unfortunately has been closed just recently. But we were still lucky to have the chance to do this type test quite a few years back. What we found for this specific kiosk substation, the transformer, and be mindful, it's all been tested after it's already been built. So we didn't have a chance to optimize much, with regards to airflow and the design of louvers. And the other request, because of horizontal rain, we had quite a challenging situation with a request for IP34 IP rating of the transformer enclosure, which certainly didn't help with the natural ventilation and just increase the enclosure class. So what we found with this kiosk substation, that it could actually only deliver about 80% of its nameplate rating. So that substation was delivering 1200 kVA instead of 1500. As a mitigation measure in this instance, the host cooling was proposed. We did another test of this same enclosure with installing the 4 ventilation fans on the roof, which actually increased the rating up to a full 1500 kVA. It's quite interesting, what Mike just recently said, that in his modeling with his design of enclosure around the old transformer, the impact of forced ventilation was actually minimal, which makes sense, because that design was fully optimized for the airflow, which probably wasn't the case for this particular substation, and the way that the switchgear and the transformer were installed, switchgear being quite large, and the cast resin transformer installed in such a way that you cannot really achieve very high air velocity. So therefore, the natural ventilation, the forced ventilation provided a much higher impact and increased rating up to, from 1200 to 1500. So that was the outcome of type testing. The good thing, though, requirement to achieve 1500, it's only in case of future load increase, and the actual loads at this moment that customer has, or when they installed it years back, there was only around 1 MVA. So it's still that kiosk substation was well sufficient even with natural ventilation, and the forced ventilation, there is more provision for the future if their loads are going to ever increase. Maybe if we look at the next slide, Nick, there's some interesting thermal scan images that we took during those type tests, which exactly shows where the hotspots are and how the intakes works at the bottom of the louvers. The hot air outputs go to the top of the louvers, and also we installed the 4 cowlings on the roof that actually helped a lot with improving that natural ventilation within this enclosure. So really, as an outcome of this test and this whole discussion, from that point we started actually specifying the output of the kiosk substation on all our offers, and this way it's simpler for the customer. Rather than going through Enclosure Class and going through all the derating graphs, we simply specify what output going to be achieved, and that was based on this test and some other calculation, extrapolation. And these days now we have even better tools with the thermal flow modeling, like Mike explained. But the important thing is really at the quotation stage is to ask a question from a customer: what is the actual required output of their substation? Therefore, everyone is aware what is required. Therefore, we can then offer a substation that will meet the requirements. And there's always a possibilities, of course, to increase the rating of the particular substation by, for example, increasing the design temperature of the transformer to compensate for the temperature rise. So maybe if you install a standard transformer rated to 40 degrees, it can only deliver 80% of the outputs. But if you increase the design temperature to 50 or 55, then all of a sudden you get 95% or 95. So that's all can be optimized upfront at the design stage.
Okay, well, I think we're just about there for today. If you have some technical questions, continue to keep sending those through, and we'll be answering those shortly. And we're making last webinar's questions and answer sheet. We're putting that on the landing page that we spoke about earlier. There were some really good, interesting technical questions on there. There's about 10 pages actually worth of questions and answers. And consultants that are listening, if you've got some graduates, you can force them to watch the webinar from last time and then go through and learn all the questions and answers. Don't forget, webinar number 3 now, update. It's going to be happening in mid-February next year. So mid-Feb, we'll come back with webinar number 3, where we'll be looking at designing for harsh conditions. All right, guys, thanks for participating today. Dimitri, wonderful as usual. Sean, great contributions always. And Mike Thornley, thank you for your input on that thermal modelling.
Thank you.
Thank you.
All right, see you later, guys, and we'll be taking some live Q&A in a second.